Hey guys, welcome back to the channel. In this video, we are going to start with colligative properties of non-electrolyte solutions, and we are going to understand the first colligative property, that is nothing but vapor pressure lowering. Now, it is better if you all know what is Raoult's law. Okay, and if you all do not know what is Raoult's law, then don't worry guys, I've already uploaded a separate video on it. You can find the link of that video in the description box below, or you can simply click on this I button which is present on the right top corner of your screen. So guys, let us start with the colligative properties. Now first of all, what is the meaning of colligative properties? Okay, so colligative properties are simply physical properties of solution. Okay, they are nothing but the physical properties of solution which are affected by number of solute particles in the solution. So guys, can I say that if any physical property of a solution gets affected by the number of solute, then that physical property is called as a colligative property. Let me repeat myself again. See, if any physical property of a solution gets affected by the number of solute, then that particular property is called as a colligative property, which means that if you change the amount of solute, that is nothing but the number of solute, then the property, the physical property which gets affected will be called as colligative property. And here you need to note one point, that colligative properties are not affected by the nature of solute. Okay, they are not dependent on the nature of solute, they are only affected by the number of solute. Clear with this guys? Now basically there are four colligative properties that we need to understand. The first one is vapor pressure lowering, the second one is boiling point elevation, the third one is freezing point depression, and the fourth one is osmotic pressure. And as I mentioned in the starting of the video, we are going to cover vapor pressure lowering in this video, and the remaining three properties will be covered in the further videos. Clear with this? Now to understand what is vapor pressure lowering, you must first understand what is vapor pressure. Okay, so for that let us consider a closed container over here. Okay, and in this closed container I am going to take a volatile liquid. Now why I have taken a volatile liquid? Because the top layer molecules of the volatile liquid evaporate even at room temperature. Okay, and as we all know that when liquid evaporates, it is going to form vapors. Okay, and guys, what you observe is that initially the liquid gets quickly evaporated into vapors. Okay, initially it is going to get quickly evaporated and it is going to form vapors. So guys, can I say that initially the rate of evaporation is fast? Okay, now guys, again after some time we make observations, and now what we observe is that the liquid is still getting evaporated and forming vapors, but this time the liquid is forming vapors slowly, which means that the liquid is getting evaporated slowly. So guys, can I say that now the rate of evaporation is decreased? And you observe one more thing, we observe that now the vapor molecules have also started turning back into liquid, and we all know that vapor molecules turning back into liquid is called as condensation. So guys, can I say that now the condensation is also started? Okay, so after some time we make two observations. The first observation is that the rate of evaporation is decreased, and the second observation is that the condensation has also started. Now guys, again after some time we will reach a stage, and at that particular stage there will be a dynamic equilibrium that is being established. Now what is the meaning of this dynamic equilibrium? So what happens at dynamic equilibrium is that the amount of liquid turning into vapors is equals to the amount of vapors getting converted back into liquid. Let me repeat again. The amount of liquid getting converted into vapors will be equals to the amount of vapors getting converted back into liquid, which means that if 10 moles of liquid gets converted into vapors, then the same amount, that is nothing but 10 moles of vapor, will also get converted back into liquid. So this is what happens at a dynamic equilibrium. So guys, can I say that at dynamic equilibrium, the rate of evaporation will become equals to the rate of condensation. Why? Because rate of evaporation tells us how quickly the liquid gets converted into vapor, and the rate of condensation tells us how quickly the vapors get converted into liquid, and both are happening at same rate, therefore they are equal. Clear with this? Now at this equilibrium, can you see still there are vapors that are being present? These vapors will apply pressure on the liquid. Okay, these vapors that are present will apply pressure on the liquid, and the pressure applied by these vapors is called as vapor pressure. Clear with this? So if we have to define vapor pressure, what will be the definition? The pressure exerted by the vapors. Which vapors? See, these vapors that are present on the liquid at dynamic equilibrium. This is the most important point. At dynamic equilibrium is called as vapor pressure. And guys, we represent this vapor pressure as P naught. Okay, please make note of this, otherwise you will get confused afterwards. Okay, so make note of this, that we represent vapor pressure as P naught. Okay, now guys, after understanding vapor pressure, now let us understand what is vapor pressure lowering. So for that, as you can see, I have considered a volatile solvent, and this volatile solvent is obviously a liquid. Okay, and I have a non-volatile solute, and this non-volatile solute is a solid. Okay, now what is the meaning of non-volatile? See, since it is non-volatile, therefore it is not going to form vapors at room temperature, and obviously there won't be vapor pressure present. If there are no vapors, then there won't be vapor pressure as well. Clear with this? And here I am having a solution of solute plus solvent. We all know when we add a solute to the solvent, we will obviously get the solution. So I have represented this solution as over here. Okay, now let's name this solvent to be A. So guys, the name of our solvent is A, the name of our solute is B, and obviously in our solution there will be A present as well as there will be B present. Now since it is a volatile solvent, therefore it will since it is a volatile solvent and it is a liquid, therefore it will form vapors, and obviously it is going to have some vapor pressure. So let's assume the value of vapor pressure to be PA naught. As I mentioned earlier, we represent vapor pressure as P naught, and since its name is A, therefore we write as PA naught. Now what will be the vapor pressure of this solute B? See, it is a non-volatile solute, therefore there won't be vapor pressure present. There with this. Now in this solution, my one simple question to you all: in this solution, who is responsible for vapor pressure? Whether it is solvent because of whom the vapor pressure is present, or whether because of solute there is vapor pressure present. Obviously the vapor pressure over here is present only because of the solvent, because the solvent is volatile and it is going to form vapors, whereas our solute is non-volatile and hence it won't contribute to forming vapors. Therefore, this vapor pressure created in this solution, above this solution, see, the vapor pressure which is being created over here will only be because of solvent. Okay. So guys, one thing is sure over here, that the vapor pressure in this solution is only because of solvent. Now, what is the name of this solvent? The name of the solvent is A. Okay. So now when this solvent is not mixed with the solute, its vapor pressure is Pa0. Am I right? When it is not mixed with any solute, its vapor pressure is Pa0. Now over here it is mixed with the solute. So what will be the vapor pressure of A in this case? Will it be equals to Pa0? Obviously no. Here the vapor pressure of A above the solution will be some different value, and this value we assume to be Pa. Okay. Now, how to find out the value of this Pa? So this we get to know with the help of the Raoult's law. So according to the Raoult's law, see, the value of this Pa, will be equals to mole fraction of A into Pa0. What is Pa0? Vapor pressure of pure solvent. Okay. See, this is Pa0. Okay. And this is Pa. Okay. So as I said earlier, what is Pa? Pa is nothing but vapor pressure of A above solution, and we all know in solution there is B also present, and we also say it as partial vapor pressure of A. Okay, this is a better word, partial vapor pressure of A. Why we have used the term partial over here? Because as you can see, along with A there is B also present. Therefore, we have used the term partial vapor pressure of A. And the sign remains the same. It is going to be Pa only. So guys, finally can I say that Pa will be equals to XA into Pa0. And let's name this to be equation number 1. Clear with this? We are going to use this equation afterwards. Now, what is the meaning of this XA? This XA is nothing but mole fraction, which I will tell you all in next 3 to 4 minutes. Just keep patience. Okay. Now guys, when we add a non-volatile solute to volatile liquid, see over here we have added a non-volatile solute to a volatile liquid. What happens is that guys, the value of this Pa0, so the value of this Pa0 will be greater than the value of Pa. Okay. See, this is Pa0. The value of this vapor pressure when it is pure will be obviously greater than the value of Pa, and this is called as vapor pressure lowering. Clear with this? The value of this A when it was pure is Pa0, and when it is added with a solute which is non-volatile, it becomes Pa, and this value of Pa has decreased. It is less than Pa0. Therefore, it is called as vapor pressure lowering, as the value is decreasing from Pa0 to Pa. Clear with this? The value has decreased. Now guys, why is it so that the value of Pa is less than the Pa0? Let's understand this. See, as I mentioned in the starting of the video, vapors are created because of the top layer molecules. These top layer molecules will form vapors. So as you can see over here, in this top layer there is only A molecules present. Okay, whereas in this top layer, as you can see in the green color, there are B molecules also present. So these B molecules are going to act as an obstruction for these A molecules, and it is not going to allow them to come to the top layer. So as there is an obstruction created by these B molecules which are not evaporating themselves and not allowing the A molecules to even come to the top layer is the main reason due to which the value of Pa is less over here. Clear with this? Okay, so I hope you have understood what is vapor pressure lowering. Now moving on guys, what will be the value of vapor pressure lowering? Obviously the value of vapor pressure lowering will be nothing but the difference between these two, Pa naught minus Pa. Okay, now let's name this to be equation number 2. So up till now we have got two equations. This is the first equation and this is the second equation. We are going to use them. Now before that, as I said earlier, I am going to explain what is this mole fraction. Okay, so this mole fraction, simple formula for mole fraction, XA is nothing but number of moles of A present in the solution divided by the total number of moles in the solution. Similarly, for XB, that is nothing but mole fraction of B, and who is B? B is nothing but our solute. So the mole fraction of B will be equals to number of moles of B present in the solution divided by the total number of moles in solution. As simple as that. Let's understand this mole fraction in a better way. Okay, so for that let's consider an example over here. And example says that in 5 moles of solution, which means that the total number of moles of solution is nothing but equals to 5. 2 moles are A and 3 moles is B. So guys, can I say that the value of XA will be nothing but 2 by 5? Why? Because there is 2 moles of A that are present out of the 5 moles, and XB is nothing but 3 moles of B that are present out of 5 moles. So this is simple as it is. Okay, so I hope you have understood what is mole fraction as well. And guys, you will observe one thing, that whenever you add XA plus XB, you will always get 1. In this example also, as you can see, 2 by 5 plus 3 by 5 will obviously give you 1. So this is the relation that you will always get. Suppose if there is some other substance C present, then XA plus XB plus XC will be equal to 1. Okay, so when you add the mole fraction of all the substances present in a solution, you will always get 1. Clear with this? Now guys, I am going to shift this XB to the right hand side. So when you shift this XB to the right hand side, the value of XA becomes equals to 1 minus XB. Clear with this? Now guys, we are going to use this relation in equation number 1. What is our equation number 1? See, XA is equals to 1 minus XB. So in this equation number 1, we are going to substitute the value of XA. Okay, so let's substitute it. This is our equation number 1, and instead of XA we are going to write 1 minus XB. Okay, as it is. Now guys, just open the brackets and multiply. So Pa will be equals to Pa naught. See, 1 into Pa naught minus XB into Pa naught, as it is I have written over here. Now guys, next step is that I am going to shift this XB Pa naught to the left hand side, and this Pa will be shifted to the right hand side. Okay, therefore this minus sign changes to plus sign, and this Pa naught, which is positive, becomes negative over here. Now guys, let us observe the second equation. The second equation tells us that the value see, delta P is equals to Pa naught minus Pa. So with the help of this second equation, instead of this Pa naught minus Pa, we can write delta P. Okay, and let's name this to be equation number 3, and we are also going to use equation number 3 ahead. Okay, so for now we have used the equation number 1, we have used the equation number 2, and we have got a beautiful equation number 3. Now when you observe this equation, guys, can I say that the value of this delta P, what is this delta P? Delta P is nothing but value of vapor pressure lowering. So delta P depends on XB, and XB is nothing but mole fraction of B. Okay, so as you can see from the formula, delta P becomes depends on the XB. So guys, in other words, can I say delta P, what is delta P? Vapor pressure lowering depends on XB, and XB depends on number of B, and who is B? B is nothing but solute. So can I say guys that the vapor pressure lowering depends on number of moles of solute. Okay, why? Because xb depends on number of moles of B, and B is nothing but our solute. Okay, so guys, as you can see over here, that vapor pressure lowering is depending on the number of moles of solute. So guys, we know that any physical property that depends on the number of moles of solute is called as your colligative property. The definition that we did in the start, any physical property that depends on the number of moles of solute is called as your colligative property. Clear with this, guys? Now moving ahead, let's understand what is relative vapor pressure lowering. Okay, now what is this relative vapor pressure lowering? Last term, guys, relative vapor pressure lowering is nothing but the ratio of vapor pressure lowering, the value of vapor pressure lowering, divided by vapor pressure of pure solvent. And we know vapor pressure of lowering is represented by delta P, and the vapor pressure of pure solvent is represented by PA naught. Okay, now further on, guys, from equation number 3, so this equation number 3, what we get, the value of delta P is nothing but xb into PA naught. Okay, so let's substitute the value of delta P as xb into PA naught. Okay, so from this, can I say that xb is equal to delta P upon PA naught? How do I get this value? See, in this equation number 3, xb into PA naught is equal to delta P. Am I right? So just shift this PA naught to the right hand side. So when it goes into the right hand side, can I say xb will be equal to delta P divided by PA naught? Okay, so this is what I have written. xb is equal to delta P divided by PA naught. Okay, now instead of this delta P upon PA naught, can I write xb? Okay, so I will replace this by xb. And what is this value? This value is nothing but equals to relative vapor pressure lowering. So in this case, can I say that the relative vapor pressure lowering will be equals to xb? Why? Because xb is equals to delta P upon PA naught. So just substitute the value of delta P upon PA naught as xb, and you will get vapor pressure lowering as xb. And as you can see over here, this vapor pressure lowering, relative vapor pressure lowering, is depending on xb, and xb depends on the number of B, number of moles of B, and B is nothing but our solute. So this relative vapor pressure lowering, since it is depending on the number of moles of solute, therefore this is also a colligative property. So guys, I hope that you have liked this video, and if you like this video, then please don't forget to subscribe to our channel and go check out my channel where I uploaded physics and chemistry videos. They might be helpful for your learners. Thank you for watching this video.